Welcome to my channel. I'm Zhang Xu. Let's look at the problem 51 in chapter 24. Chapter 24 is about capacitance, dielectrics, and electric energy storage. There, we need to show the function of the electric energy stored in electric field outside of an isolated spherical conductor of radius r. This is r. Is equals to this function, right? The first way is ask you to do this work in three ways. First way is consider energy density. So how can we do that? First one, we write down the equation for energy density is 1/2 epsilon naught E squared, right? This is the electric energy per cubic meters, right? Agree? Yes. In this function, you can say epsilon naught is constant. E is electric field density, right? So it's very straightforward. If we want to consider energy density, we need to write down the electric field density outside of conductor E in this function. We did this work in Gaussian's equations, right? You can check your previous chapters. Now in this function, you can see energy density is get. Now we can say if we want to find the electric energy, we can do the integral with the energy density to its volumes. Do you agree? Yes. So it looks like if we want to find electric energy, use the integral, the energy density times dV. dV is the derivation about the volumes, right? So how can we write the dV? We can consider the volumes for this spherical conductor, right? It's 4/3 pi r cube, right? In this way, very easily, you can get dV as 4 pi r squared dr. Now you can see U and dV is get, so we input U and dV inside, right? And then the E, we input it inside. E is not, so input the E inside, we get the function look like this one. And simplify it, we can get the function look like this one, and do the integral, you get answer there. The second way is now together with the capacitance of an isolated spherical. So the B way, we can see now tell you can use the capacitance of these spherical conductors to find the electric energy. How can you do that? So easy, right? For this case, if you want to find electric energy, you just use the charge squared divided by 2C, right? This C is the capacitance for the spherical conductor. Now tell you can use this function for capacitance for the spherical object or spherical conductor. So there you can write down this capacitance at there 4 pi epsilon naught r and input the C inside. You get the answer there. The third one asks you by calculating the work needed to bring all the charge Q up from the infinity in the very small bits dq, right? Yes. So how can we do that? We can see in this case the potential for the small particles that like Q is just Q over 4 pi epsilon naught r. Do you agree? Yes, this is for Q. And then if we want to find electric energy, that is equals to the work is needed, right? And the work is needed, we can use the potential times the charges, right? And this charge is just the small fraction of charges dq. So we can find the small fraction of the energy as V times dq. Do you agree? Yes. Now we input the V inside. It looks like this one. Now you can see you can do the integral, right, for this equation. And the dq, you can see at initial it's 0 on this conductor. And finally it's Q, right? So we do the integral from 0 to Q. Then you get the final answer there. Thank you.